So it will be preparation number 5, I believe.
Yes, sir.
From alkenes. So the topic still remains same, preparation of alcohols. Preparation of alcohols. From alkenes. Okay. Now, there can be two ways of preparing the alcohols from alkenes. One follows Markovnikov's addition and the other follows anti-Markovnikov's addition. So the one which follows Markovnikov's addition, we first proceed by that. Number A, by acid catalyzed hydration. By acid catalyzed hydration. Now, what is the meaning of the term acid catalyzed hydration? It means that you are adding of water in the presence of an acid. So that is the meaning of acid catalyzed hydration. So if you consider any alkene and treat this with water in presence of an acid as a catalyst, then there will be addition of water around the C double bond C in this manner. Because it's a symmetrical alkene, there is no problem in addition as such. Why? Because you don't need to follow any Markovnikov's rule, as there is possibility of only one particular product that is formed. So symmetrical alkenes do not require any Markovnikov's addition. And if it is asked that why the catalyst is required, the catalyst is required because alkenes in general are nonpolar and water is a polar medium. So nonpolar and polar will not interact. So we have to create some disturbance in the alkene. And that disturbance is created with the help of the H plus coming from the acid. And that is why we say that the presence of acid is important for creating the disturbance. So say, for example, we have ethene treated with water in presence of a suitable catalyst. The product will be ethanol, CH3, CH2OH. It will be ethanol. Now let us see what is the mechanism of the reaction. What shall be the mechanism of the reaction? Mechanism comes because it is part of the syllabus. So there are various steps involved in the mechanism. But first, we need to understand that the H plus that is produced from acid will be protonated by water, resulting in the formation of H3O plus. So whenever a proton is given by any acid, it gets hydrated, or we can say that water gets protonated and water accepts the H plus, and this H3O plus or hydronium ion is actually the source of attack. So this is the alkene on which the attack is to take place. This is the hydronium ion, which has oxygen positive charge on it. So what this carbon, any one of the carbon can invite the H plus. So suppose it invites the H plus. And in order to invite the H plus, obviously, the electron cloud should move towards oxygen, resulting in the formation of this product. So hydrogen has been added up around C double bond C. So if you notice one thing, that around the C double bond C, one of them will be taking the hydrogen and the other will be taking the positive charge. And you get a carbocation produced, and water will be the byproduct. So try to visualize each and every point. Again, I am repeating, the H plus given by the acid is taken away by the water, producing hydronium ion, and that hydronium ion actually supplies the H plus. And when it supplies the H plus around C double bond C, one of the carbons will be taking the hydrogen and the other will be taking the positive charge. Then comes step 2. In step 2, the carbocation that is produced will be attacking the water again. So we have produced the carbocation, and it is going to attack which part of water do you think will be attacked by the carbocation? This is water. So which part of water do you think will be donating the electron to the carbocation? Yes. Who is electron rich in this water?
Oxygen.
Oxygen, of course. So oxygen will be donating its electron, one of its electron pairs, to the carbocation, thereby developing positive charge on it, and accordingly oxygen again becomes positively charged. Again becomes positively charged. So when oxygen becomes positively charged, it is again unstable. So to make it stabilized, what it is supposed to do, it is supposed to, we'll go to step 3 to understand the next step.
Sir, can you repeat the step 1 again?
Step 1, H plus is given by the acid, and that
Yes,
H plus is taken by water. So water, after taking the H plus, becomes H3O plus, hydronium ion, which is source of proton actually. And when this proton from the water, I mean from H3O plus, is taken by C double bond C, you get the water back and proton gets into the C double bond C. One of the carbon around the double bond will develop positive charge, and another carbon will invite the hydrogen. Okay.
Okay, sir.
Now the one which develops positive charge again combines with the water, forming bond with the oxygen of the water, and oxygen again becomes electron deficient. So in step 3, this unstable species to save itself takes away the electron from the hydrogen again, thereby producing the alcohol. And H plus is again taken by the water. So this H plus actually will be the part of the water. See, if you go through the NCERT book, this mechanism has been made confused by including water. So because the H plus is associated with water, so therefore it becomes very confusing and it becomes very difficult. So first you write down the steps, because these are the steps that are given in the NCERT book. I'll give you another alternative to understand the same reaction. You first complete the steps, then I'll give you another step to understand the reaction. Done?
Yes, sir.
Okay. Now, rather than writing this, if you don't want to show water, there is another alternative, and that is relatively easier. So let us see what is the other alternative for it. Suppose you have an alkene and it is treated with acid in aqueous medium. So rather than writing H3O plus, you can also write H plus within bracket AQ. So when it will be inviting H plus, one of the carbon will get the share of hydrogen and other will get the share of positive charge. In the next step, it is going to attack the water and oxygen will try to form bond with it, resulting in the formation of an unstable species. And finally, because oxygen is unstable, so again it is going to take out the H plus, thereby forming this product. I think this is more easier. Just see. Which steps you are more comfortable with, the first or the second?
So second.
The second.
Second one is more easy. Because in the second one, I have not shown water, but within bracket, I have put AQ. So accordingly, one will be inviting the hydrogen, other will be inviting the positives. Now here, you don't have any choice because the alkene is symmetrical. But if it is unsymmetrical, then what will happen? Let us try to understand. Complete this first. Because as such, even though the mechanism is included in the syllabus, but term 1 comprises of only multiple choice question, assertion and reasoning. You will not be asked to write the mechanism, but still you remember the steps involved. Okay, written down. Can I move on?
Yes, sir.
Okay. Now let us see what happens when the alkene is unsymmetrical. Suppose we take propene and treat this with water in acidic medium. Then there are two possibilities. If hydrogen comes to this, OH will come here. And if hydrogen comes to this, OH will go there. So let me write down both the possibilities. This is possibility number 1. This is possibility number 2. But it has been found out that out of 2 possible products, this is not formed at all. Only this one is formed. It follows the Markovnikov's rule, according to which the positive part of the water, which is hydrogen, will go to that carbon around the C double bond C, which contains more number of hydrogen. And the negative part will go to that which contains lesser number of hydrogen, isn't it? This is what is
Yes,
Markovnikov's rule? Yes. So what is the reason behind it? Why do you think the positive part goes to the first carbon and the negative part goes to the middle carbon? That can be understood with the help of the mechanism. So I have told you that when an unsymmetrical alkene invites the H plus, there are two possible intermediates theoretically. What are the two possible intermediates? The first possible intermediate is if H comes here, the positive will be developed at the corner. And this will be the product. I mean, this will be the intermediate. And what is the second possibility? If H comes here, the positive charge will be developed in the middle carbon. Now, out of these two, which do you think is more stable and why?
Sir, second one.
Second one is more stable. Why? Because this carbocation is 1 degree or not?
yes, sir.
This carbocation is bonded to only one carbon. What is there thereafter, we are not concerned with this, but this is bonded to only one carbon. And this is bonded to how many carbons? 2 carbons. Isn't it?
Yes, sir.
Yes, sir.
Okay. So obviously, if you have two different ways of formation of product, which product will be preferred? The more stable one, isn't it? As I always give you the example that you have two ways of coming down from the top story building. Either you take the staircase or lift, or there is a better way, you can directly jump down. Will you prefer the second method? Will anyone prefer the second method? If staircase and lifts are available, will anyone jump down?
No,
No,
sir.
sir.
No,
Of
sir.
course no. Why? Because you know that if you jump down, so you will be unstable. So nobody takes that pathway, though that is the fastest pathway. But we should not always look at the fastest pathway. We should look at the stablest pathway. Now this can also be formed, this can also be formed, but this will not be formed because this is less stable, this is more stable. So we will discard this. We'll take only this. So in the next step, the carbocation will be this. The carbocation will be inviting the water. Oxygen of water will try to form bond, becomes unstable, and thereafter it is going to lose the H plus. And when it loses the H plus, the only product form will be propan-2-ol. Understood or not? Why this product is preferred? When would have this product formed? This product would have been formed if this was the stable intermediate, isn't it? Because wherever there is positive charge, there the attack of the water will be taking place. But we know that this is less stable, so this will not be formed. This is more stable, this will be formed. Clear?
Yes, sir.
Okay. So whenever you are treating these unsymmetrical alkene with water in presence of some acid, the alcohol produced will follow the Markovnikov's rule. which proceeds via more stable carbocation during the course of the reaction. Written down, can I proceed?
Yes, sir.
Okay. So what we can write down under this, by acid catalyzed hydration of alkenes, alkenes add up water in the presence of dilute acid to produce alcohols. Alkenes add up water in the presence of dilute acid to produce alcohols. In case of unsymmetrical alkenes, the addition follows Markovnikov's rule. In case of unsymmetrical alkenes, the addition follows Markovnikov's rule. So first you take symmetrical alkene, treat this with water in the presence of acid, you get alcohol. But if it is unsymmetrical, it will be unsymmetrical. In unsymmetrical, Markovnikov's rule will be followed. Understood?
Yes.
So out of the two, where the Markovnikov's rule is followed and where it is not followed?
In the second one, Markovnikov rule is followed.
In the second one, the Markovnikov's rule is followed. Why? Obviously, because
it's
it's an
unsymmetrical.
unsymmetrical alkene. Yes. Clear? So with the help of mechanism, I have explained why one type of product is preferred over the other in case of Markovnikov's rule. Can I proceed?
Yes, sir.
Okay. Now, under the same topic, that is from alkenes only, if you want to produce anti-Markovnikov's product, just as in case of haloalkanes, we had the possibility of producing both by peroxide effect. We were following the anti-Markovnikov, and simply by adding HBr, we are getting Markovnikov's product. So here also, we can produce the anti-Markovnikov's product, which is just reverse to that of Markovnikov's product. And the name of the process is by hydroboration oxidation reaction. by hydroboration oxidation reaction. You don't require the mechanism for it because relatively it is complicated and it's not required for the syllabus also. But still remember that when you take an unsymmetrical alkene like that of propene, and remember the reagents. Reagent number 1 is diborane, B2H6. And reagent number 2 is hydrogen peroxide in basic medium. The reagent looks complicated, but actually this reagent ultimately helps to add up water according to anti-Markovnikov's rule, which means that now the OH will come at the first carbon and H will go to the second carbon. So hence we can say that depending upon where do you require the OH, accordingly you'll have to give that particular reagent. Let me give another example so that the thing is clear to you altogether. In both the cases I have shown propene. Now if you have propene treated with water in presence of H plus and diborane followed by hydrogen peroxide in basic medium, what kind of product you are going to get in the first reaction? Markovnikov or anti-Markovnikov?
Markovnikov.
Markovnikov. So accordingly, the OH will come at the middle carbon. And if you are carrying out hydroboration oxidation reaction, same water will be added up, but following anti-Markov. So this much you need to understand, that whenever hydroboration oxidation reaction is carried out, the OH will always prefer the outwards carbon. And when it is treated with water in presence of H plus, then it follows Markovnikov's, and the heavier group will always try to get inwards, will try to attack the inner carbon. Clear?
Yes, sir.
So write both the reactions together to get the difference. Okay, can I proceed further?
Yes, sir.
Okay. So altogether, we require 5 methods of preparation, starting from haloalkanes. Then we carried out the reaction with the reduction of aldehydes and ketones, then reduction of carboxylic acids and esters. The fourth one was very important. It was a reaction between Grignard's reagent and aldehydes or ketones. And under fifth one, that is from alkenes, we got 2 types. One is following the Markovnikov's rule, when alkenes are added to water in presence of acid, and the other was anti-Markovnikov's, when it is hydroboration oxidation. Can I rub it? Is it clear? Done?
Yes.
Yes, sir.
Okay. So this brings to the end of preparation of alcohol part. And after this, we'll talk about physical properties of alcohols. Physical properties of alcohols. So just as we discussed about physical properties of haloalkanes, and we gave more importance on 2 topics. One was boiling point and the other was solubility. So let us see that how alcohols behave towards their physical properties. First of all, we talk about boiling point. When you compare the boiling point of the parent alkane from which all different types of organic compounds are synthesized, haloalkanes and alcohols, it has been found out that if they have comparable molecular masses, the boiling point is increasing from alkanes to alkyl halides to alcohols. So the question arises that why haloalkanes had higher boiling point with respect to alkanes. The reason was simple. It is because the haloalkanes are polar. Alkanes were non-polar. And polar molecules have greater intermolecular forces of attraction, because of which they can show dipole-dipole attraction. They cannot show dipole-dipole, rather they show weak van der Waals forces. Now, when you compare haloalkanes with alcohols, the alcohols have been found to show greater boiling point, which of course cannot be explained on the basis of polarity because both molecules are polar. But if you look at the magnitude of the polarity, so let me tell you that this alcohol has got very high polarity, because of which it is capable of showing what is called as intermolecular hydrogen bonding, which the haloalkanes were not capable of showing, because in order to show intermolecular hydrogen bonding, not only you should have highly electronegative atom, but it should be attached to a hydrogen atom as well. So hence we can say that due to the capability of the alcohols to show intermolecular hydrogen bonding, they show stronger interaction and therefore they have greater boiling point. So you can write down that alcohols have higher boiling point than both alkanes as well as haloalkanes of comparable mass due to their capability of forming intermolecular H bonding. So if you have alcohols near to each other, so you will see that they can show intermolecular H bond. So the red broken lines that I have shown are intermolecular H bonds, which bring the alcohol molecules close together, resulting in the formation of increased boiling point. Clear?
Yes, sir.
Now coming to the second point. So this was the comparison of alcohol done with other functional groups. But within alcohols, among different alcohols, boiling point increases with increase in molecular mass. So molecular mass is the second factor. So if all are alcohols, of course, you cannot compare them on the basis of intermolecular H bond because all can show intermolecular H bond. But here, you'll have to decide on the basis of what is called as molecular mass. So therefore, boiling point increases in the order CH3OH less than CH3CH2OH less than ... So as the molecular mass keeps on increasing, the boiling point will also keep on increasing. Okay?
Yes, sir.
What about isomeric alcohols? Isomeric alcohols means alcohols which have same molecular mass but different structural formula. So we have already discussed during the haloalkane topic among isomeric alcohols, boiling point decreases with increase of branching. So as we have already discussed that as branching increases, what will happen? As branching increases, surface area will decrease or increase?
Decrease.
Surface area will decrease. And if surface area decreases, so it will be facing lesser van der Waals forces of attraction. So suppose we have different types of tertiary butyl alcohol, different types of butyl alcohols. This is tertiary butyl alcohol. This is secondary butyl alcohol. This is isobutyl alcohol. And this is N-butyl alcohol. So who do you think out of the four will have highest boiling point? Which has minimum surface area? Out of the four, who do you think has minimum surface area and least boiling point?
Tertiary.
Tertiary has maximum branching, so therefore it will have minimum surface area. And if the surface area is less, the boiling point is less. So don't you think the tert butyl alcohol will have least boiling point and N-butyl alcohol will have highest?
Yes, sir.
Yes, sir.
So it is same as that of what we discussed in haloalkanes topic as well. Nothing new. The only difference is here we have OH group instead of X. Rest, more or less, all the concepts that we have been using remains the same. Clear? The points regarding boiling point?
Yes, sir.
Yes, sir.
So if it is asked that why alcohols have higher boiling point than haloalkanes, the reason for it is because alcohols can show intermolecular H bonds among themselves. Haloalkanes cannot. And among alcohols, obviously, the points that we have discussed was also discussed in case of haloalkanes, that with increase in molecular mass, boiling point will increase. Among isomeric alcohols, more the branching, lesser will be the van der Waals forces and lesser will be the boiling point. Okay.
Yes, sir.
Okay. So after the boiling point, we move on to the second important physical property, that is solubility. So we had already discussed in last chapter that haloalkanes are insoluble in water or partially soluble in water. It means that they have very, very poor solubility in water. What is the reason? Because the concept is, when you mix up two liquids A and B, and if you want that A should be miscible with B, then the amount of energy that is released when A interacts with B should be higher than the amount of energy required to break A bond A and B bond B. Because until and unless the older bonds are broken down, older interactions are broken down, you cannot expect new interactions. And in case of haloalkanes, we had seen that the amount of energy released when haloalkane interacts with water was not large enough to break haloalkane interaction or water interaction. But if the haloalkane is now replaced by alcohol, let me tell you that alcohol water interaction is stronger than water and alcohol interaction, and therefore when alcohol interacts with water, the amount of energy released is much higher and sufficient enough to break the interactions between water and alcohol. Understood? Please tell me if not understood.
So can you repeat?
Sir, can you repeat?
I'm repeating it again. If you are mixing up two molecules and you want it to be soluble with each other, the rule is the amount of energy released when they are mixed up should be high enough to break the older interactions when they were in the pure state. Clear?
Yes, sir.
Okay. Now, in case of haloalkane, which interaction was strong? In pure state, the interaction was strong, or in combined state, the interaction was strong?
Pure state.
Yes. In pure state, the interaction was strong, and when they are mixed up, the interaction was not strong enough to break the older bonds. But in case of alcohols, when water and alcohol are mixed up, the interaction is quite high, and therefore the amount of energy released is sufficient enough to break the older interactions. Clear?
Yes, sir.
Yes, sir.
Okay. So this is what we are going to write. Lower alcohols are highly soluble in water due to their capability of forming strong intermolecular H bonds with water. Okay. So if this is alcohol,
Sir, what is written after highly?
highly soluble. Highly soluble in water due to their capability of forming strong intermolecular H bonds with water. So if you have alternatively alcohol and water molecules, so previously when alcohol was in pure state, you had alcohol H bonding or water H bonding. But when they are mixed up together, you will have alcohol-water H bonding, which is stronger than that of both alcohol and water H bonding. So as a result, they get mixed up very well with each other. And therefore, we say that lower alcohols are highly soluble in water. However, the solubility of alcohols decreases with increase in molecular mass due to increased hydrophobic alkyl group. Now, this is very, very important point. See, alcohols are denoted as R bond OH. Which part of alcohol is responsible in becoming soluble in water? R or OH?
OH.
So we say that OH is hydrophilic, isn't it? But R, which contains only carbon and hydrogen, it's a non-polar part. It is not loving water, so it is hydrophobic. Now, as you keep on increasing the molecular mass of an alcohol, which do you think grows? Is it R or is it OH?
R.
R. OH remains same, whether it is ethanol, methanol, propanol. So R is growing in size. If R grows on, keeps on growing, it means its hydrophobic character is increasing or not?
Yes, sir.
Yes, sir.
And if hydrophobic character increases, so its solubility in water will increase or decrease?
Decrease.
Decrease.
It will decrease. Understood?
Yes, sir.
So alcohols with greater molecular mass will have lesser solubility in water as compared to alcohols with lesser molecular mass, because I told you the reason why. It is the hydrophobic R which keeps on increasing. Clear?
Yes, sir.
So,
Any point which you think, there are so many students in the batch, please clear out your doubts, because you have to minutely learn the things.
Sir, sir, R O H to alman buzai dibo niki?
Etu buji poa nai?
Sir, last banai.
R is what? What exactly is R containing?
Last ki.
Okay, I'm not getting your point because you're not audible, but still I'm repeating the whole thing. Alcohol comprises of R and OH. All alcohols can be represented as ROH. R is alkyl group, which comprises of only carbon and hydrogen. And as carbon and hydrogen forms the non-polar part, so therefore it is hydrophobic. And it is the OH which is responsible in forming intermolecular H bonds with water, and therefore this is hydrophilic. This part interacts with water, not this part. So as a result, we can say that out of the two, who has more dominance, that will decide its solubility in water. If this is more dominating, then this will be more soluble. If this is more dominating, it will be less soluble. Now, as the molecular mass increases, the growth of R continuously moves on. OH remains same. So obviously, as R keeps on increasing in size, its solubility in water will decrease or not?
Yes, sir.
Understood? This is what has been said. Yeah.
Okay, sir.
Point number next. Among isomeric alcohols, solubility in water increases with branching. Can anybody explain me this? Why solubility in water increases with branching? It's a very simple concept. Just think and tell me what can be the reason. Anyone?
The surface area increases.
Surface area increases with branching?
Or decreases.
Huh? If surface area decreases, why do you think there will be increase in the solubility in water?
So interaction decreases between them.
Okay. So here we have tertiary butyl alcohol and we have N-butyl alcohol. Who do you think is more soluble in water according to this statement?
N-butyl alcohol.
First one.
First one. Okay, so first one is more soluble than second one. So this is branched and this is non-branched. Now, what will happen when there is branching? When there is branching, the surface area decreases. And if surface area decreases, the alkyl group will have lesser dominance or not? It is the alkyl group whose surface area is decreasing, isn't it?
Yes, sir.
So if dominance of alkyl group decreases, automatically the dominance of OH will increase or not?
Yes, sir.
And if dominance of OH increases, will it not be more soluble in water?
Yes, sir.
Is it clear to everyone? Kshitij?
So can you repeat?
This alkyl group has more dominance or this alkyl group has more dominance? You will calculate on what basis? You will be calculating on the basis of surface area. Who has greater surface area, the first one or the second one?
The second one.
Second one. Now, if its surface area is more, it means its hydrophobic character will be more or not?
Yes, sir.
And its hydrophobic character will be lesser or not?
Sir, how?
Because its surface area is decreasing. Alkyl group's surface area is decreasing means what? Its dominance is decreasing or not? It is less spread out.
Okay, sir.
So if this is less dominating, so automatically it will be more soluble in water or not? Because if the dominance of this is less, automatically the dominance of OH will be more. Yeah.
Yes, sir.
And that is why we say that among isomeric alcohols, solubility in water increases with branching. More the branching, less dominating will be the alkyl group, and the characteristic will be more determined by OH, not the alkyl. I hope this point is clear.
Yes, sir. Yes, sir.
So tert butyl alcohol is most soluble butyl alcohol and N-butyl alcohol is least soluble alcohol in water. Why? Because tert butyl is most branched having least surface area and least dominance of hydrophobic alkyl group. But N-butyl alcohol is just the opposite, where the alkyl group has maximum dominance. Clear?
Yes, sir.
Okay. So these are the points to be understood under physical properties of alcohols. So boiling point and solubility are two important aspects that we need to understand. Okay. After discussion of physical properties of alcohols, we now move on to chemical properties of alcohols. Chemical properties of alcohols. Alcohols are represented in this manner, where you see that oxygen is a highly electronegative element, and it is capable of taking away the electrons both from the carbon as well as from the hydrogen. Obviously, it will not take away the electrons from both at a time. It can take electron from R also, and it can take electron from H also, one at a time. Now, if it takes away the electron from R, let us say, and this bond is undergoing cleavage. Let us name this bond as A and this bond as B. So if the cleavage point is A and oxygen is working through the blue arrow, then what do you think will be the cations and anions produced if R loses away its electron towards oxygen?
R plus OH minus.
Very good. R plus OH minus. And R plus is carbocation. And we know that carbocations are electron deficient species. But if the cleavage point is B, then what do you think will be the cations and anions produced? Yes?
RO minus plus H plus.
Excellent. RO minus plus H plus. And RO minus is called alkoxide ion, which is electron rich. It is alkoxide ion. Is it understood what I have just now said?
Sir, could you repeat?
Oxygen is more electronegative than both carbon as well as hydrogen. And in alcohols, as we know that oxygen is present in between, so it is capable of taking away the electron both from the carbon as well as from hydrogen. Not at a time, but one at a time. Now, if the oxygen takes away the electron from the R part, so H will be along with oxygen. So will it not break down into R plus and OH minus?
Yes, sir.
And if the cleavage occurs in oxygen-hydrogen bond, so R will be along with oxygen or not?
Yes, sir.
So what will be the product? Is it not RO minus plus H plus?
Yes, sir.
Okay. So if the cleavage occurs in carbon-oxygen bond, we get carbocation. And if the cleavage occurs at oxygen-hydrogen bond, we get an alkoxide ion. Clear?
Yes, sir.
Okay. Now the question arises that alcohols are basically subdivided into three types: 1 degree, 2 degree, and 3 degree. If someone asks me that which type of alcohol will prefer this type of cleavage and which type of alcohol will prefer this type of cleavage, so we will have to look at the sign this particular ion is possessing. So who do you think, which alcohol do you think will prefer to form the carbocation the most?
3 degree.
3 degree. Why? Because carbocations are electron deficient, and greater the number of alkyl groups surrounding the carbocation, more stable will be the carbocation, and that is why the reactivity order will be 3 degree, greater than 2 degree, greater than 1 degree. Why? Because the carbocation is most stable for 3 degree and least stable for 1 degree. Clear?
Yes, sir.
Okay. Come to this one. Here, this ion, alkoxide ion, is already electron rich. And if you have more number of alkyl groups, then it will be destabilizing the alkoxide ion, isn't it?
Yes, sir.
Yes, sir.
Previously, it was hungry of electron, and therefore, more the number of alkyl group, better it is for it, because they are feeding more and more electron to the hungry carbocation. But here, this is not hungry, it is already fed up. It has already taken its food. And after taking food, if someone keeps on forcing you to take more and more food, so it will destabilize you or not?
Yes, sir.
Yes, sir.
So who do you think this particular, which alcohol will be showing the fastest reaction towards it?
1 degree.
1 degree alcohol.
1 degree, greater than 2 degree, greater than 3 degree. Yes, anyone having any doubt, please clear it out. Anyone? Any doubt
No,
regarding
sir.
this? Clear, na?
Yes, sir.
Yes, sir.
Kshitij, is it understood?
Yes, sir.
So hence, alcohol can show both type of reactions where it undergoes cleavage both in carbon oxygen bond as well as oxygen hydrogen bond. But the reactivity order will differ from alcohol to alcohol. 3 degree will prefer to show cleavage in this manner where cleavage point is A, and 1 degree will prefer this type of cleavage where cleavage point is B. Now, if someone loses OH minus ions, what will you call it? What are the substances which lose OH minus ions called? Hmm? Okay. What? What are the substances which lose OH minus ions are called?
Bases.
Bases. And what are the substances which lose H plus ions are called?
Acid.
Okay, acid. So which alcohol do you think is most basic and which alcohol do you think is most acidic? Which alcohol is showing this particular reaction fastest? I have written the order, no?
3 degree.
3 degree. So 3 degree alcohols are most basic. Three degree alcohols are most basic. And 1 degree alcohols are what?
Most acidic.
Most acidic. Among alcohols, we are making the comparison. It means that alcohols are amphoteric in nature. They can act both as an acid as well as base. But when their basic character is compared, so obviously 3 degree is most basic. And when their acidic character is compared, 1 degree is most acidic. Understood this much?
Yes, sir.
Okay. Yes, should I rub it? All of you are clear about this? Okay. Now, my question goes to everyone, and individually I'll ask you because not all of you are participating. Water loses H plus ions to produce H plus and OH minus. Alcohols loses H plus ions to produce H plus plus RO minus. My question to you is, out of water and alcohol, who do you
So
think
shouldn't
is
it be
more
ROH instead of RO-H?
ROH? So the question arises that out of water and alcohol, who do you think is more comfortable in losing H plus? And accordingly, who is more acidic out of water and alcohol?
Alcohol is more acidic.
So according to you, alcohol is more acidic. Abhinandan, you tell me, who do you think is more acidic? Abhinandan has gone to kitchen for taking food. Anushwa, who do you think is more acidic, alcohol or water?
For alcohol.
According to you, alcohol. Arisha,
Sir, alcohol.
alcohol. Bitopan, Chandana,
Sir, water.
water. According to you is more acidic. Okay. Jumi,
So water.
water. Jyotirmoy,
So ROH.
okay. So some of you are saying alcohol, some of you are saying water. Tell me, out of hydroxide ion and alkoxide ion, who is more stable?
Sir, water.
No, out of these
Carbocation.
two, who is more stable? RO minus or HO minus?
Sir,
H
OH minus.
minus.
HO minus.
HO minus.
Yes.
Does oxygen require electrons?
No, sir.
No. But R is a plus I group or not? Will it not push further electron to O minus?
Yes, sir.
Yes, sir.
Yes, sir.
Ultimately, out of these two, who is less stable? This one is less stable, na?
Yes,
Yes, sir.
Yes, sir.
yes, sir.
Okay. If this is less stable, that means out of these two reactions, as this is less stable, the tendency of going in the forward direction will be more or less for alcohols.
More.
Sir, less.
If I tell you that if you go to that place, it is full of danger and you may kill yourself, will your tendency to go there will be high or low?
Low.
Low.
Low. So if I say alcohol, don't break down, because if you break down, it will lead you to very unstable species. So its tendency to break down will be high or low?
Low.
Low.
Low. So who has higher tendency of breaking down to give H plus?
Water.
Alcohol.
Water.
Water.
Yes, water. So accordingly, who will be more acidic out of alcohol and water?
Water.
Water.
Water. Understood?
Yes, sir.
Water has relatively greater acidic strength than alcohols, as OH minus is more stable than OR minus. Clear or not?
Yes, sir.
Yes, sir.
And among alcohols, which alcohol do you think is most acidic? 1 degree, 2 degree, or 3 degree?
1 degree.
1 degree. Because here we want lesser alkyl group. Because more the alkyl group, it is going to make the reaction slower, isn't it? Because we get less stable alkoxide ions. Is that clear up to this much?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
So these are basic things which we need to understand, that whenever you are asked to compare any acidic strength or basic strength, so for acidic strength, we'll break it down to give H plus and compare the resulting ion. If the resulting ion is less stable, so its tendency to lose that particular ion will be automatically lesser. So move on to the next topic, chemical reactions. Of alcohols. Chemical reactions of alcohols. So under chemical reactions of alcohols, we will categorize reactions into 3 types. Reactions involving cleavage of R bond OH. Will these reactions be acidic reactions or basic reactions of alcohols?
Basic.
Basic reactions. And accordingly, what will be the reactivity order? 1 to 3 or 3 to 1?
3 to
3
1.
to 1.
So in all these reactions, 3 degree alcohols react the fastest, 1 degree react the slowest. Reactions involving cleavage of RO bond H. What is the reactivity order? This is an acidic reaction. Yes.
So 1 degree greater than 2 degree greater than 3 degree.
And the last one is reactions involving ROH as a whole. No individual bond will be breaking down, but as a whole, the reaction will be taking place. So hence, we categorize the chemical reactions of alcohols into 3 types. Reactions involving cleavage of R bond OH, reactions involving cleavage of RO bond H, and reactions involving ROH as a whole. Okay?
Yes, sir.
Can I proceed?
Yes, sir.
Yes, sir.
So now we are going to talk about those reactions where the cleavage is taking place in between R bond OH. And interestingly, all the reactions have been already discussed during preparation of haloalkane. So I'm writing down only the reactions and just see whether we have done these reactions or not. Under this, we first talk about reaction with halogen acids. When alcohols are treated with HCl in presence of anhydrous ZnCl2, you get RCl plus H2. When alcohols are treated with HBr in presence of concentrated H2SO4, or better I write KBr. Can anybody tell me? It will confirm whether you are actually studying or not. When it is Ki, what should I take instead of concentrated H2SO4? Can we take concentrated H2SO4 or should I take something else? And if I take something else, who should it be? Anyone? At least Jyotirmoy should be able to answer quickly. Yes. What should be
Sir,
the
for
acid
me,
taken?
the board is blur. I can't see it clearly.
My question is, you are able to get my voice?
Yes, sir.
My question is, when you are preparing RBR, you are making use of KBr plus H2SO4. But when you want to prepare RI, so along with Ki, what acid should I take? Can we take H2SO4? So we should take phosphoric acid, H3PO4. Details of which have already been discussed during preparation of haloalkanes. You can consult. So these are the reactions with halogen acids. We can prepare all different types of haloalkanes, RCl, RBr, RI, depending upon what particular reagent is to be used. Then we discussed about reactions with phosphorus halides. Reactions with phosphorus halides. How many types of phosphorus halides are there? Yes. How many types of phosphorus halides are there? No answer. I'm not getting your voices.
Sir,
Is there a
4.
network? 4 types of phosphorus halides. What are they? Phosphorus halides can be 2 types, either trihalide or pentahalide. Okay, now if it is PCl5, the product will be RCl plus POCl3 plus HCl. If it is PCl3, the product will be RCl plus H3PO3. But in case of phosphorus bromides, there can be only tribromide. And in case of phosphorus iodide also, you will get triiodide. I don't know whether I get this answer from you or not. Why pentabromide or pentaiodide is not possible? Chitil? Why PBr5 or PI5 is not found? Can you tell me?
No, sir.
Anyone? Because all these things have been discussed. That is why I'm asking you. Why pentabromides and pentaiodides are not formed? Okay, you can go through those videos, and if you have written it down, see, chlorine is relatively smaller in size or not?
Yes, sir.
Yes, sir.
And
Yes,
bromine
sir.
and iodine are large sized atoms. So phosphorus cannot hold 5 bromine or 5 iodine together. And that is why pentabromides and pentaiodides are not formed. I also told you that if you want to get PBr3 and PI3, they have to be prepared in situ. So for that, we will have to take red phosphorus and bromine. We'll have to take red phosphorus and iodine. Okay, so these are the reactions with phosphorus halides. Have you written down the reactions with halogen acids list?
Yes, sir.
Okay. Now I expect at least one answer from this third reaction, because this is a very, very important question. Number 3, reactions with thionyl chloride. SOCl2. Why do you think the preparation of alkyl chlorides are preferred by this method from alcohols? Can anyone tell me? Why do you think the preparation of alkyl chlorides from thionyl chloride and alcohol is preferred over all previous methods?
So pure alkyl halide is formed, so SO2 and HCl is formed in the gaseous form.
You get RCl. Along with RCl, what else is produced?
SO2.
SO2.
SO2 plus
SO2 gaseous, HCl gaseous. So what will happen if the byproducts are gaseous? They will escape out or not?
They will
They will escape out. And if they escape out, what they are leaving behind?
RCl.
RCl in pure amount, isn't it? So that is why it is preferred over other methods. All 3 reactions we have actually done during the preparation of haloalkanes. The only thing is, if you revise it, if you go through those classes, then the thing will be more clear to you. Okay, should I rub it?
Yes, sir.
So during all these reactions, what is happening? Is it not the carbon OH bond breaking down?
Yes, sir.
Okay, so in all these reactions, which alcohol do you think react the fastest?
Three degree.
3 degree, because I have written in the topic itself that all those reactions where the cleavage is occurring between carbon and oxygen, the reactivity order is 3 degree greater than 2 degree greater than 1 degree. Okay, clear?
Yes, sir.
Yes, sir.
Now we move on to the second type of reaction. Reactions involving cleavage of RO bond H. So which alcohol will react the fastest?
1
What is
degree.
the order of reactivity is 1 degree greater than 2 degree greater than 3. So these reactions are new to us. So we will talk about it in details. But because previous all 3 reactions had already been discussed during preparation of haloalkanes, so therefore I did not go into the details. To first talk about, we'll talk about reactions with metals. And these metals should be highly reactive, like sodium, magnesium, aluminium. And during these reactions, what will happen? Alcohols react with highly electropositive metals to produce the respective metal alkoxides along with liberation of H2 gas. So when alcohols are treated with sodium, when alcohols are treated with magnesium, and when alcohols are treated with aluminium, so depending upon the valency of the metals, sodium is monovalent, magnesium is divalent, aluminium is trivalent. So accordingly, that many alcohol will react. The first one will give you sodium alkoxide along with liberation of hydrogen. Second one will give you magnesium alkoxide. Hydrogen will be liberated as usual. And third one will be aluminium alkoxide. So in every case, hydrogen is getting liberated. So hence we can say that all electropositive metals, highly electropositive metals, sodium, magnesium, aluminium, they have the tendency of removing the hydrogen from alcohols as hydrogen gas, and they will form the respective metal alkoxide. RONA is sodium alkoxide, RO(2) magnesium is magnesium alkoxide, RO(3) aluminium is aluminium alkoxide. So what kind of nature is shown by the alcohols during these reactions? Is it acidic reaction or basic reaction? Yes,
Acidic.
acidic. How do I know that these are acidic reactions? Because of course, alcohols are leaving their hydrogen when treated with metals, and metals have basic character. So a base will react with acid to form salt, but it's not a hydroxide, it's a metal. So along with the metal alkoxide, which is a kind of salt, hydrogen gas is getting liberated. Okay. Written?
Yes, sir.
Yes, sir.
So after reaction with metals, under the same topic, we now talk about a very, very important reaction. Reactions with carboxylic acids. So mark this. The process has a name called esterification. And as the name implies, esterification stands for production of esters, which means that when alcohols react with carboxylic acids, during this process, esters are produced. Esters have a very special characteristic. They all are sweet smelling, fruity smelling compounds. And during their production, just with the help of smell, you can make out that esters are produced, because of which the reaction can be used as a test for alcohols as well as carboxylic acids. When alcohols are treated with monocarboxylic acids, in presence of concentrated sulfuric acid. When alcohols are treated with monocarboxylic acids in presence of concentrated H2SO4, sweet smelling esters are produced. This is alcohol, RO bond H. I am showing according to the cleavage taking place. This is carboxylic acid. I am writing in a reverse manner. And when it is treated with concentrated H2SO4, which is a dehydrating agent, it removes the water in such a way that alcohol loses the hydrogen and carboxylic acid loses the OH. Accordingly, the ester will be R-COOR plus, of course, water. What is the characteristic of esters? Tell me. How do you know that esters are produced?
Sweet smelling.
Sweet smelling, fruity smell. Fruity means mango fruity, no? Fruity means like a fruit. Hence, the above reaction can be used as a test for detecting OH group in a given compound. So in organic practicals, we have this under detection of organic functional groups. So if you are given a liquid and you test the presence of OH in it, so we'll simply react it with a known carboxylic acid like acetic acid. And if after some time you get sweet smelling coming out, it can be conferred that esters have been produced. And because esters have been produced and you have added acetic acid, so obviously this must be an alcohol. Clear or not?
Yes, sir.
Yes, sir.
So if someone asks you that what is the test to detect the presence of OH group in a given organic compound, the answer is, one of the answers is esterification. So esterification can be carried out. Okay. So today I stop it here and we'll further continue whenever I take the next class. So what is the next type of reaction remaining? How many types of reactions we have
involving
discussed so far?
ROH as a whole.
ROH as a whole. Okay, so those will be special reactions where individual bonds will not be breaking down, but as a whole, the molecule will take part in the reaction, and that we will continue. Thank you. Good night, all of you.
Thank you, sir.
Thank
But
you, sir.
all of you, please study because organic, you have to be in continuous touch. Otherwise, it's very easy to remember and easy to forget as well. So please revise the things. Okay. Okay. Good night. Thank you.
Thank you, sir.